I don't know.
Because why would you name something that sounds like the exact same thing?
It's a good question. I don't know. I'm going to go ahead and say hyperbola.
You're supposed to know these. What kind of educator are you? You can't educate us.
Stop complaining. All right. So yesterday we talked about this. That we talked about the geometry of an ellipse, and we said that the geometry of an ellipse was it's a collection of points that are equidistant, or no, they're the sum of the distances to the two foci is constant. Okay, and the key word in that phrase was the sum of those distances was constant. For a hyperbola, it's really just a minute change in that definition, but the shape of the thing changes drastically, though. Instead of sum, it's difference. Okay? So, it's a collection of points, again, whose distances to two fixed points, again called foci, have a constant difference. Okay, and the equation of a hyperbola is formed based on this definition. And I'm not going to go through all of that with you because it's lengthy and it wastes a lot of time. However, as with most things, if you're interested in learning more about this and want to see that actual proof of why it is what it is, your textbook does an excellent job of showing that to you. And it's on page 656. They do a little proof, do some algebra, and do some simplifying at the end, and they end up with this equation for a hyperbola that looks something like this. Yep, that's exactly what it is. The sum turns into a difference, and the same thing happens in the equation by the time you go through the whole proof of it, and it looks like this. X squared over a squared minus y squared over b squared. That's a little issue that comes about now because of the fact that we have a minus sign instead of a plus sign. With an ellipse, it was always a is bigger than b, right? Nope. A doesn't have to be bigger than b, and b doesn't have to be bigger than a. Because with an ellipse, when you add those two terms together, it didn't matter what order you did it, really, right? The x could come first or the y could come first as long as the bigger number was under the one that was in the major axis, right? And so we could just shuffle it around. This one I can't shuffle because subtraction, the order matters, right? And so the bigger one doesn't always go under the same.
A is always first and B is second.
Yes. A always comes first, B always comes second, but they're not, regardless of size. Exactly. It doesn't matter which one's bigger. Sometimes A is bigger than B, sometimes B is bigger than A. But I'll show you here in just a second on a graph how you actually find A and B, though, because that is important because you need to know which is which off of that. Yeah?
Will A always be under X?
No. Yeah, this one has two different ways that it's going to go, too. Could be this.
You have y squared over A minus X squared over B.
This would be the other one. Y squared over B squared minus X squared over B squared equals 1. So what did stay the same with those two? A always comes first, B always comes second. Okay, so A is always, with the first fraction, B is always with the second one. Now that's not the case with ellipses. Now if you notice, every time I did an example with ellipses though, I always put the A first. It was always in the first fraction. I just happened to write it that way. I made the bigger one come first. Though mathematically I didn't technically need to do that. I did that though so it wouldn't be confusing to you once we got to this. If you always make your first fraction have the A on the bottom, whether it's an ellipse or a hyperbola, you'll be fine. It will still work. Okay? Though technically with an ellipse you could have swapped them if you really wanted to, but you don't need to. Okay? The orientation is affected with this. Kind of like with an ellipse, we have a major axis and we have a minor axis. And if I write it this first way, the major axis is along the x-axis. If I write it the second way, the major axis is along the y-axis. Okay? But they look a little bit different. So I'm going to draw a sketch for each of these of kind of how they look. Okay, so a hyperbola. It's got a center. Both of these, so far I haven't shifted around the centers at the origin. Okay? So put a little X at the origin. That's where the center is. And it's got two foci. That's my major axis is the x-axis for this one. Be somewhere to the right and left of center, like that. But by switching this thing from a constant sum to a constant difference, it looks like this. It's actually in two pieces. That's what a hyperbola looks like. So any point that you find on that hyperbola, you measure its distance to one focus, its distance to the other focus, and you subtract, you'll always get the same number, no matter where you measure it from.
How do you know which order to subtract?
Big one minus the little one. So if you're talking about the difference in two distances, you always want to do the larger minus the smaller, right, technically. Otherwise, you'd get the same answer. It would just be negative. But if we're talking just, I want to know the difference between the two, you would then just do larger minus the smaller. So that's always going to stay constant. Okay, so that's the orientation for an x squared over a squared style hyperbola. Okay. Now, if I switch that up and now it's a y squared over a squared, it's probably about what you would expect. Instead of the hyperbola opening left and right, it opens up and down. Okay, it looks the same. It's just been kind of rotated up 90 degrees. Again, center is still at the origin. Got a focus up here somewhere and a focus down here somewhere. These are going to open up and down. Like that.
So is the distance from like the start of the hyperbola always the same distance from like its origin or center?
No. Good question. Oftentimes people, based on the way these things are drawn just generically, get a little confused about some distances in here. This is not halfway. Is that what you're asking? This is not halfway between the focus and the center, necessarily. It could be. Sometimes they are. But not always. It doesn't have to be. Okay? It's just, it has to be in between them somewhere, though. Okay? It is the same on both sides. It is symmetric, though. Yeah. So it is the same distance apart from things from one side versus these are vertices. Are not halfway between the focus and the center, though. Not necessarily. Okay, so where the heck is the A? Where's the B? All of that kind of stuff. Okay? Well, here's the thing. You can't physically see the B. You can see A, you can see C, but you can't see the A, or you can't see the B. Okay? Sorry, it's getting... You can see C. Carbon copy. Anyway. So, there's A. Both of these distances to a vertex is A, along the major axis. And that definition of A is exactly the same as what you had for an ellipse. From the center to a vertex along the major axis. Okay? Okay. We'll chat about B in a little bit. Like I said, you can't really physically see it. C, as an ellipse, distance from the center to the focus, to each focus. Okay? So in this case, and there. And those are the same, right? Symmetric on either side. Yeah. So here's one major difference between hyperbolas and ellipses with the whole ABC thing. In an ellipse, A was always the biggest measurement, right? And it was always bigger than C, because the foci were inside the vertices, right? So the foci were closer to the center than the vertices were. Hyperbola, it's like you've unfolded it and it's out the other way now. So now the vertices are closer to center than the foci are. So A is always going to be smaller than C. Okay? So you should probably jot that down because that's kind of an important thing. Mm-hmm. Yep. So, since you brought it up, we might as well talk about it. We can do a quick little chat. So electricity, remember, was C. A. Exactly. You guys all see that? Because the foci are actually further away from the center than the vertices, that means C is greater than A. But if C is greater than A, that fraction has to be bigger than 1. Right? If it's exactly 1, that's a parabola. If it's exactly 0, that's a circle. Okay? So
How does 1 make a parabola?
we'll talk about that later. But let's no. E equals 0. We'll talk about that later. And again, as E gets larger down this list here, the shape of some of these conic sections. An ellipse is kind of the closest thing to a circle we have, right? And then a parabola, well, just hear me out. This is kind of loosey-goosey, I know, but a parabola is less like a circle than an ellipse is. You guys can all agree with me on that one, right? It doesn't even close. It just keeps going up. And then a hyperbola is not only like one parabola-shaped little piece. It's actually got 2 of them, both all going away from center rather than kind of rotating, orbiting around it. So that's even less like a circle. I know that part I had to kind of fudge a little bit. But anyway, as far as eccentricity is concerned, though, that's kind of sort of the idea, though, is you become less and less circular. And as we get to polar equations of conics, which we'll study next week, like I said, eccentricity plays a major role in that game because we have a generic polar equation for any conic section, and part of that equation that we use has E in it. And so you have to know what kind of conic section E so that you can take that number and drop it into the equation and come up with the correct polar equation to do it that way. So we will come back to that later. How does having a focus on the vertex?
Focuses on the vertex that
Mhm.
is 1.
If C,
E and A are the same. Distance from the focus to the distance. How does that make a parabola, not 2 parabolas?
so if you C to, I hear what you're saying. So if you were to move,
Then E is equal to 1.
mhm,
Parabola.
it deals with that whole directrix definition of it. Just like I said, just wait for it, because I don't want to get too far away from what we're talking about right here. But it does. It does. So what to do about B? Let's go back to that for a second, because we haven't talked about that. So if I make an equation of a hyperbola, I need to know B, right? It's part of the equation. So I need a way to calculate that. Okay. Well, squared, right? Because A was the largest measurement. Now, A is smaller than C. So does this equation make sense anymore?
B squared over B squared plus A squared.
So now it's back to is this regular pyramid?
It is.
Like I said, you teach us something.
I'm not screwing it up. This is absolutely correct.
Let's screw it up. This is the one that makes most sense.
Yeah, now we're going to screw it up further.
So, probably. It happens. So, hyperbolas is your regular used to a squared plus b squared equals c squared because the distance from the center to the focus is the largest measurement on there. And so that's got to be the one that it's equal to like that. So, yeah, you can always write these so that it goes A, B, C. You just have to move the equal sign around a little bit. To do then is we can find B. And then we can use that to come up with an equation. As long as we know where the center is, we know where the foci are, where the vertices are, we got everything we need. Okay? So, real quick, we'll keep it centered at the origin for right now. So let's say a hyperbola has vertices 0 plus or minus 4 and foci 0, and I got to make them further out, so plus or minus, let's say 7. What is the equation of the hyperbola? Okay. So we need to know orientation. We need to know what's A, what's B, and we're good. That's it. Okay? So, what's A? Four. Okay, and I also need to find B, but I don't know that yet. However, I do know C. C is 7. So if I follow my hyperbola Pythagorean theorem here, 4 squared plus B squared equals 7 squared. So 49 minus 16. Feel free to leave that as the square root of 33 because it's easier when you go back and plug it in. And then we also need to know orientation. So is this hyperbola opening left and right, or is it opening up and down? Up and down. Now think about the geometry of those points you were given. It's 0 plus or minus 4, 0 plus or minus 7. So those are going up and down, right, from the origin. So this one's going to open up and down. So we got an up-down. So that's going to be our second equation I showed you here. All right, so let's make sure we've got everything where it needs to go. So we've got y squared over 4 squared, 16, minus x squared over b squared, which would be what? 33, that's why we left it as a square root, equals 1. So,
Wait, why did we even square root that if we're just putting b squared underneath that?
I don't know. I guess you could have just left it b squared, whatever. Now, there is a physical use for just b by itself we'll talk about in a little bit, but yeah, for this equation, you probably didn't need to. Now, just wanted to make you notice something again here with this one. We talked about how a does not need to be bigger than b, right? And this one is exactly doing that, right? A is actually smaller than b in this case. A is 4, b is the square root of 33, so the first number is not bigger.
Actually represent.
Well, let's talk about that. B is a way, B by itself, well, it's a measurement that helps determine how fat or how skinny your hyperbola actually looks. give you an example. So like, let's say all we know is A and E, and we don't have anything to do with B. So maybe our vertex is here, vertex is here. Okay. So then the question becomes, or maybe it's a little better than that. Than that even. Yeah, and eccentricity does tell you how stretchy it is, but E doesn't give you a means directly to graph the thing correctly, though. It does tell you about how stretchy it is, but there's no way to really take that number and do anything with it. The B does give you a way to figure out how stretchy this thing is, if you're being nice and neat about how you graph it, too. If you're not, something that's a little off. So, I'll give you an equation of a hyperbola. We're going to do a graph of it. We're going to use B to help us figure out how stretched out it should be. There's my glitch for, that's my glitch for the day. All right. Okay, x squared 9 minus 1 squared over 16 equals 1. So what are the values of A and B? A is 3, B is 4. And if you did 5. A squared 25, right? Yeah. Make it the same as the y scale as far as the spacing goes, otherwise this might not look quite correct. So let's plot some of this stuff. So the vertices, A is 3. Remember, center's at the origin still here, right? So center's out through, or the area. I know it's going to open left and right around those foci, but again, how stretchy is it? Okay. Well, we can create a couple of asymptotes here to help us graph. If you guys recognize this or not, hyperbola, really a fancy reciprocal function. It's a rational function, but it's been turned a little bit. Okay, we're used to seeing rational functions done in such a way that they look like. Come up over here for just a second. The ones look like this, right? But if I turn it, see how that's technically a hyperbola? The center's right here. Here's a focus. Here's a focus. It's really just a hyperbola.
Do they follow the same rules?
They do.
Could I find focuses,
Mm-hmm.
foci on the rational function?
You'd have to rotate the axes, though, which is the next section we're going to look at.
Okay.
Can't do that in this section, but rotating axes. Okay, but for this one, How do we get those asymptotes? Well, the asymptotes in this one, notice how they're vertical and horizontal, but if I have it twisted like this, now they're going at angles. Okay? So my asymptotes here are going to be, it's going to be like a big X right through the middle of this thing. Okay? So to figure out what exact equations I need for those two asymptotes, or about what are their slopes, that sort of thing, how far are they, we're going to make a little box to help us do that. And here's where B comes into play. Out to a vertex here. B, kind of like before, is going up and down on the y-axis. Okay, B is 4. So we're going to come up to here to 4 and down here to -4. Those 2 points, as we have seen, are not on the hyperbola though, right? It's not part of the curve, but they're just kind of like guide points for us here to help us out. So if you start with these 4 vertices, or these 4 points, go straight up and over, and then straight up and over. And we're going to make this big rectangle. No, you're right. They're not. Those are not the asymptotes yet. Let's find the asymptotes, though. Remember I said the asymptotes are going to make like a big X in the middle? Exactly. So I was careful about how I did this. I should be able to go through the origin and go corner to corner with these things. These are the asymptotes. Well, their slopes are using A and B, right? Correct. Yes, they do. Yeah, if I move this thing, which we will in a little bit, if I move these hyperbolas, then the center will not be the origin anymore. But for right now, yeah, it's at the origin. So I might need to make these come out just a little bit more so it's easier to follow. The idea is that the hyperbola should be approaching those asymptotes as they go out. So one side of it and the other side. To see about how stretched out it is. And in this case, it's pretty stretchy, right? They're not squeezed down quite so much. They're vertically stretched a little bit more probably than you anticipated. But that's the idea. That's how we use B to help us out. Okay? So B is not a direct measurement of anything on the hyperbola, though it does have something to do with it, though. It helps us to draw it. That is the slope of those asymptotes, right? So these asymptotes, for this. What are the slopes of those 2 asymptotes? Rise over run. You're almost there. It's not A over B. It's B over A. Plus and minus B over A, right? There's 2 of them. Okay. Now, not to throw too much at you at the same time here, but see if you can do this. What if this hyperbola did not up and down? What would be the slopes of the asymptotes then? What did you say? Plus or minus A over B in that case. Okay? Because when I take that hyperbola and I turn it, remember A is measuring along the major axis. No. It's vertically, right? Up and down. Okay? So of that asymptote is now A, right? Up and down, rise, and then the run is the B. Okay? So is going to be. Okay, so okay, you can always just sketch the thing and look at it and do it that way and find the slope of the asymptote that way. But if you're more of a formula, algebra type person and you want a little equation to use, there you go. It's always that way. Okay. So let's try one where we actually move some things around a little bit. So we're not centered at the origin anymore. If we can get through this, then we'll call it. Yep. All right. It's a graph of y minus 2 squared over 25 minus x plus 1 squared over 16 equals 1. Yep. Careful about the order there. Yep. Negative 1, 2 would be the center. What's the value of A? What's the value of B? 4. Okay. And is this up, down, or left, right? Up, down. Right? Oh, if we want to do the foci, I guess, on there, we'd have to find C as well. So that would be 25 plus 16 is 31. No. 25 plus 16 is 41. So C would be the square root of 41. Graph it effectively. What is that? About 6 point something. 6.35. I got 6.4. All right, 6.4. Mm-hmm. Keep in mind up and to the left. And we got to get out as far as at least 6. So I'm going to go. These, just so you know, like on a test or quiz or whatever, I have a coordinate plane already on there for you. Okay. We'll see. I might end up needing a little extra space here yet. Start here. Center is keep that straight. That's a center, and that's not a vertice or a vertex or a focus or something like that. All right, and it's an up-down, and so we need to use A to get to the vertices. We need to go up and down 5. So the 6.4. I use my B to make the box again, so I can get an accurate look at how stretchy this thing is. What?
I thought the both side was 6.4 off the
Center.
yeah.
Yeah. So B, and then, so it'll- and then and so this like something like this. There it is.
Necessary to graph the asymptote in order to graph the hyperbola.
If you want an accurate graph, yeah. If I ask you for a sketch, you don't need to have the asymptotes. If I ask you to graph it, you do, for sure. Yeah. So, guys, think we can do this if I were to move them around on you? Okay. Tomorrow we're going to do some of that. We're going to do some more completing the square. Going to talk a little bit more eccentricity, that sort of thing, and then we'll be wrapping it up. Okay, so picking up from yesterday with hyperbolas here, there's a little bit of vocab I want to show you guys with hyperbolas. Just like with ellipses, we have this major and minor axis type thing. But with hyperbolas, sometimes they use a different lingo. So I wanted to show you that first, and then we'll use that language to analyze them a little bit. Thank you. Thank you. All right, so zoom this in a little bit so we can see it better. So the major axis which normally it would be this right here, right, with a hyperbola. Okay, so that's called the major axis. It is also called the transverse axis. This is just with hyperbolas that they call it that as well. I don't know, honestly. And then when you were making, remember how we were finding the asymptotes and we were making that little box that was like this with B? Okay, and so then we had this kind of like invisible axis that we called the minor axis, but it was only used to make that little box. We could figure out where our asymptotes were going. So that we still referred to as the minor axis. But that has another name too, called the conjugate axis. I don't know. Okay. The only reason I'm showing these to you is because your textbook likes to use them. They refer to the two axes as the transverse axis and the conjugate axis, but I was always taught you still call them major and minor and just call it good. So, and I've seen this before, like when I've been looking at hyperbolas, working with other stuff when I was in college, and okay, transverse and conjugate, got it, whatever. I don't know why there's a need to change it, okay? Maybe you can Google it or something, or I'll research it and find out, but I never really had much motivation to figure out why. I just saw, oh, they start calling it these two things as well. Okay, whatever. But I'm just letting you know, just so when you come across that, if it says like the semi-conjugate axis or the semi-transverse axis or something like that, half the transverse, half the conjugate, whatever, they're going to use that as well. Okay, so we're going to use like some of that lingo to help us analyze some stuff here. So let's say that I have a hyperbola that has transverse axis endpoints at 3 and -7, 3, and the conjugate axis has a length of 10. So I'll give you some information kind of like that, and then find the equation of the hyperbola. Okay, and that should be everything that you need. Whoops, other way. Because think about what an equation of a hyperbola looks like. You need to know, wrong button. You need to know the A, the B, and the center. And that's pretty much it. So if you know the length of the major and minor axes, or transverse and conjugate axes, and you can pinpoint where the center is, which you can do with this, you've got everything that you need to make that equation then, right? So where is the center of this particular hyperbola? If the transverse axis endpoints are at 5, 3 and -7, 3, what's right in the middle of that? -2, 3. No. -1, 3. There we go. Okay. And if -1, 3 is in the middle, we should be able then to figure out A, right? Because A comes from the major axis or the transverse axis, right? So what is the value of A then? Six. Yep, good. 6. Okay. Axis has a length of 10, so what's B? 5. Good. Okay. Technically, what's the only other thing I need to know about this hyperbola?
Left and right.
If it's left and right or up and down, and which way is it? It is. Well, I've heard left and right now. I've heard up and down as well. Do we have a consensus? Visualize where those points are. 5, 3, and -7, 3. Is it opening left and right or up and down? Left and right, yeah. Figuring out how far the center is from the transverse axis endpoints. Each is 6 away from that. Okay? All right. So if it's a left-right hyperbola, what's coming first? The x. Okay, so it's going to be x plus 1 squared and y minus 3 squared, like that, equals 1. And so then, remember with hyperbolas, the a is always the first, right? So our a squared would be 36, and the b squared, 25. Got it. Okay, so does that process make sense? Okay, doing kind of the same thing we were doing at the end of class yesterday, just threw in some transverse conjugate axis lingo in there as well, but still all kind of the same stuff there with that. All right. So I think you guys are good. Just remember, they might, as part of the question that they're giving you here, they might throw something in there involving eccentricity as well. So don't forget that fact. I'm not going to do one like that because I don't want to spend the time doing it. But they might throw in a, hey, the eccentricity of this hyperbola is 4 or something. And then if you already know C or A, that gives you a means to find the other one. That's all they do that. That's the only reason they do that. So just remember, you can use that as well. That little equation for eccentricity will come into play. But I'd rather have you guys have more time to work. So, so let's get back to this completing the square business. So let's say I've got 25y squared minus 9x squared minus 50y minus 54x minus 281 equals 0. With an ellipse? Yeah, pretty much. You're just going to have to be a little bit more careful because with a hyperbola, you're going to have a negative sign in there to contend with because your final equation is going to have a minus in it. So if you look at this, there's a way that you can just stare at this equation before you do anything and recognize the fact that it's a hyperbola and not an ellipse. What's the difference? Where's the subtraction? That's in this one. That wouldn't be in the other one. But in front of the squared terms. Yeah, with an ellipse, both your squared terms will be positive to start with. With a hyperbola, one of them's positive, one of them's negative. So looking at this, you could probably even tell me which way this hyperbola is opening, left, right, or up, down, because the minus sign is in front of the x squared, so it's going to be an up-down hyperbola. Yeah. Mm-hmm. If both of them are negative, you would end up with an ellipse again, because then you'd factor out a negative and both become positive. Yeah, so that would have to have the correct sign on it, otherwise it wouldn't be a conic section anymore then. Or at least it wouldn't be an ellipse or a hyperbola, because you can't have it equaling something negative that way. So, okay, so let's take a look. So we got to complete the square again, so I'm going to just do, it's the same as before. So let's do a little term rearranging here again. So 25y squared minus 50y plus something. Then we've got minus 9x squared minus 54x plus something equals 281 plus something. Okay. So then if we go through each one, the y's, what am I going to have to do here to begin with those guys? Yeah, take out a 25. And that would be it. Yeah, then half of this squared is a plus 1 for that. Now here, these two, what can I take out? Yeah, and bring the negative along with it. So if I take out a negative 9, I've got x squared plus 6x plus 9 to complete that square. So yeah, what exactly was added? 25 and then a negative 81. So whatever 25 minus 81 is, that's what we should be adding over here. So negative 56? Okay. Alrighty, so let's complete our squares here finally. So this is y minus 1 squared minus 9 times x plus 3 squared. And what does this come out to? 225, perfect. Okay, and then I got to divide everything by 225. So how many times does 25 go into 225? 9. Okay, so think about that for a second. Then how many times does 9 go into 225? 25. Okay. And that equals 1. So there you go. So then we can go ahead and analyze that hyperbola then. Okay. And like we said from the outset, just by looking at the way the thing was set up, we were pretty certain this was going to be an up-down opening hyperbola. And lo and behold, yep, the y squared term is first here. The a is 3, the b is 5. So I could go through, I could graph this thing if I wanted to, all that same stuff we've been doing with these. We could then go ahead and take care of from here. Okay, so makes sense? It's using the same process as before, just doing it with a hyperbola now instead. So, all right. I think our time is used just letting you guys dig your teeth into this stuff. So I'm going to stop and let you have a look at it, okay?